next speaker's name is George Romanek, and he will be giving a presentation titled Artificial Intelligence-Based Investigation of Severe Thunderstorms Producing Downbursts in Canada.
Thank you very much for the introduction. So, good afternoon, everybody. It's a great pleasure to be here and present this research. My name is George Romanek. I come from McGill University, Department of Atmospheric and Oceanic Sciences in Montreal, Canada. In my research group, we do research on severe storms, particularly downbursts and tornadoes, urban boundary layer processes, and applications of atmospheric sciences to other fields. In this presentation, I'm going to present research of my PhD student, Mohammed Hadavi, who unfortunately couldn't be here. So here I am, presenting research I didn't do. That's a life of a university professor for most of the time. Now, here is machine learning investigation of environments in Canada prone to downbursts. So what are downbursts? These are intense downdrafts that descend from a thunderstorm. They hit the surface, spread radially in all directions pretty much, and can create very high intensity winds. So the diameter of the downdraft can be anywhere between a few hundred meters to 3-4 kilometers. The outflow velocities can exceed 75 meters per second, which is equivalent to EF3 rated tornadoes. And the issue with downbursts is not just that winds are intensive, but the vertical profile of wind speed is what we would say non-conventional. It has no shape vertical profile of wind speed, so it means that maximum velocity is occurring between 50 to 150, 200 meters, which is completely different to typical extratropical cyclone or hurricane high-intensity winds. But most buildings or any infrastructure really is designed for atmospheric boundary layer winds. So there is a lot of work that needs to be done to improve resilience of our communities to tornadoes and downbursts, not just because they have very strong winds, but the profiles are non-conventional, what we would say. So here is an example of a microburst from Nevada. Microbursts are downbursts with the damaging outflow below 4 kilometers. You can see how this event is very localized. So unfortunately, therefore, we don't have many measurements. And that's the main problem in investigation of tornadoes and downbursts. And even if we do have a meteorological station over there, few-minute averages, 10-minute average doesn't mean anything. You really have to have high-intensity anemometers, high-frequency anemometers. Now, in our work from 2022, we demonstrated that windstorms were the major cause of damage in Ontario and Quebec in Canada. So in particular, they were responsible for approximately 64.8% of all natural disasters in these two provinces. So that includes wildfires, earthquakes, if there were any. But overall, wind is the most disastrous natural event over there. And then we wanted to classify to see what type of wind events are responsible for most damages. And we classified events into convective storms, winter storms, tropical cyclones, and tornadoes. Tornadoes, so blue is Quebec, red is Ontario. Tornadoes cause a lot of damage. In fact, per event, tornadoes cause most damage. Tropical cyclones, not so much in this period, 2008-2021. Winter storms with intense winds cause significant damage in Ontario, but indeed convective storms dominate 67-68% of the overall damage. And downbursts fall under the category of convective storm winds. So then we got motivated to carry out research in which we wanted to see if we can identify environments prone to downbursts in Canada. I would like to emphasize that downbursts that we are going to base these results on are only those that cause damage. So this is a busy slide, and I'll try to guide you through it. In the top left, your left, you see NTP data, that stands for Northern Tornadoes Project data. That's basically Canadian severe storm database from 2017, sorry. But in addition to tornadoes, they also document downbursts. But they only document those downbursts that created damage. So the data set is biased to damage and also biased to populated areas, because if nobody lives somewhere where damage happened, there is nobody to report it. CLDN stands for Canadian Lightning Network. We use lightning as a proxy for thunderstorms. It was very nice to have this presentation prior to mine. And we divide the data, by we, I mean my student, and I'm here presenting. So the data are divided into downburst and non-downburst classes, and then for each of these, the analysis data profile, vertical profiles of wind, the temperature, all variables were obtained, quality checked, and using public package Thunder Air, he calculated over 200 instability indices. And then the data set was split into 80-20, 80 for training and validation, and then testing the last 20%. Now the issue here is something that many of us are familiar, is this balance in the data. Because downbursts are rare events, there are only 306 samples, and there are almost 20,000 samples of thunderstorms without recorded downbursts. So the student had to look into various resampling methods. Some of them tend to decrease the number of oversampled categories, some of them increase the undersampled category, and let me just go back actually. The machine learning models that he tested were logistic regression, Gaussian naive bayes, random forest, and support vector machines. And as seen in previous presentations, it will turn out that random forest is indeed the most reliable. Anyways, going back, you can see these various resampling methods on the x-axis, and the SVM smooth method provided the best improvement of MCC, Matthews correlation coefficient, when coupled with random forest model. You can also see that some models, such as logistic regression, actually performed the best when no resampling was introduced. That's the first set of bars. Now, in terms of critical success index, we once again demonstrated that random forest has the best performance. You can see that critical success index is something like specific humidity in atmospheric sciences. You are measuring true positives compared to everything else, like mass of water vapor compared to the mass of total moist air. Now, this diagram is also something we saw many times in previous presentations, so I don't have to go and describe it in details, but the point is that you want to be in the top right part of this graph. That's where you have the highest success ratio, as least as possible false alarms. And we can see once again that random forest model coupled with that particular smooth resampling technique provides the best results. Now we are actually predicting a little bit severe downbursts, which is not good. But when we are talking about extreme weather, if we have to make a mistake, it is better to have false positive, yes, than perhaps false negative, because you will rather say that there is going to be a very severe downburst, nothing happens. Well, maybe people are not happy, but life continues. But if you say nothing will happen, and then a very severe downburst destroys something, well, that's not very good. Now, there are machine learning is quite often black box, so it can happen that the model gives good results for maybe non-physical reasons. So there are various techniques to test for physical interpretation and significance of observables in these models. One of them is accumulated local effect and permutation importance. I'm going to talk only about the first one for the sake of time. So local accumulated effect is how much basically probability of detection of severe event, in this case downburst, increases if one of the important observables changes value. So the x-axis is cold pool strength, which is the best observable that we detected in terms of detecting downbursts, that we found in terms of detecting downbursts in Canada. So you can see as the cold pool strength, which is basically temperature between the outflow and the ambient atmosphere, as it is increasing, the probability of detection of downburst by the machine learning model is increasing. In the background, you see a histogram of just relative frequencies of these various values. Now, this was tested for various other instability indices and parameters, and we can see that in all cases there are physical tendencies and trends, which is very good, means that the model is following some sort of physics that at least we are aware of. Particularly interesting is also that in the in the bottom left, theta E, which is equivalent potential temperature difference between surface and the middle of the troposphere, is very good indicator of downbursts, and that was demonstrated already in 1990s in the MIST project in northern Alabama by Watkins and Akimoto. And we see in Canada completely different climatology. This parameter is still very robust. There is another parameter over here, DEI, which is not diversity, equity, inclusion parameter in this particular research, but rather downburst environment parameter that was proposed in one of my previous papers. Although I was leading the paper, the parameter was proposed by the second author, Professor Tazarek, and it's a parameter that actually performed exceptionally well in the United States. We tested it now in Canada, and it seems to perform quite well as well. So if you are in the downburst business, I suggest you check this parameter that combines cold pool strength and maximum wind shear. To summarize, oh, I just noticed there is a time here. Okay, so very good. So to summarize, so windstorms in Canada are most severe weather hazard, and convective storms in particular, that comes from previous research. To my knowledge, this is the first machine learning attempt to try to diagnose downbursts in Canada, so there is much more research that we need to do. Of course, we are lacking data, and there is nothing we can do but to let time pass to have more data. What we can do is also to apply this model to actually forecast. What we applied it is reanalysis data, but we can also try to apply it to forecasts. And in terms of thermodynamic parameters, the most reliable predictors were cold pool strength, moisture flux, and equivalent potential temperature difference, not just that a difference between surface and mid-levels. And in terms of composite parameters, it is the downburst environment index. Thank you very much.